Uh, a warm greetings to everyone. My name is Prachi Kashikar and I am a PhD student at IIT Goa. So today I will be talking about model compression for the edge AI. So I will start with the problem statement. I will continue the proposed solution. I will show a couple of results and the references will follow. So problem statement I would like to explain with the help of a couple of pictures. So when we are having our high-end CPUs or GPUs which are having a huge memory support and continuous power supply, so we can train giant neural networks on them without considering about the availability of underlying resources. Now when these trained networks, when we want to deploy them on small hardwares, so these small hardwares lack in the availability, or they have very stringent budgets of at least memory and power batteries always. So the option remains is to compress these giant networks and form a small neural network and then deploy it on the hardware. So in this process, some accuracy may be compromised, may be or may not be. Before compressing a model, one needs to identify what all are the factors which are impacting the size of a model. So these factors are nothing but the parameters which include weights, bias, channels, etc. Then feature maps, specifically during training, a lot of feature maps are being generated. And all these values inside computer memory are being stored in the form of floating point values. So a couple of existing methods are also showing some decent results on model compression. For an example, quantization, pruning, knowledge distillation, etc. So the very highly identifiable pitfall of all of these techniques is that some amount of accuracy is being compromised. So we are coming up with the technique which will not compromise any accuracy but will compress a model for the deployment on small edge. IEEE standards are widely accepted by computer architecture community to represent floating point values in the computer memory. Say for example, here a single precision floating point format is shown, where every floating point value is a combination of a sine, exponent and mantissa bits. Here the exponent field is of 8 bits, which means that it can take values ranging from 0 to 255. But in general, these trained neural networks are having billions of weights. So essentially, many of them are having common exponent values. So we propose to store the existing exponent values only once and then refer them with the help of some indexing method. So this is the case where we can justify our approach. In this chart, we have plotted the exponent frequency distribution of the weights of LeNet, where on the y-axis you can see that exponents are plotted, and it is clearly visible that out of all 256 different possible values of exponents, only 6 to 10 of them dominate the total frequency distribution. Now this is the proposed method. Consider here we are having 6 different floating point format numbers having only 3 different exponent values, E1, E2 and E3. So we propose to save these distinct values inside a separate table which will have its own indices. Now we are proposing to replace all exponents from IEEE standard with the respective indices from exponent table, because of which the total length of any floating point number will come down from 32 bits to something lesser. So this index field will now totally be dependent on the length of exponent table we are getting for every layer in a network. So yeah, these are our preliminary results. So we have trained different models on different data sets, and we could see that the compression we have achieved is between 9 to 10% in all of the cases. So now on the sequential reading processors like CPUs, there is some impact in the execution time, because we are reading the same number from multiple locations. But when we are targeting a hardware like FPGA, where we can parallelly read multiple values from different locations, the impact on execution time is seen as less than 1%. There are a couple of observations to be noted here. The compression depends upon the degree of distinctness in the exponents of weights. Then layer-wise compression gave better results than compressing a model as a whole. And our method has preserved accuracy while compressing a model to at least nearly 10%. And also we do not require any kind of fine tuning. So yeah, these are our tools. Thank you. Thank you so much.